All right, so this is the lesson on slope point form, which is just another way of expressing the equation of a linear function. This is probably the most, or one of the most algebraic lessons of the entire course. And so I do recommend when you're looking through the notes to pause it a lot, to write things down as you go. There's a fair amount here. And like I said, in terms of the entire course, this is at least right up there with one of the most algebraic lessons. The first thing I want to do is I want to take the slope formula, which you can see right here, and rearrange it into a different form that what we call the slope point form. And it allows us to find the equation of any linear line if we just know the slope of a line and a single point. That point doesn't have to be the y-intercept. So far, to find the equation of a line, we've needed the slope and the y-intercept. But what if we just have some other point? So first, let me just take this. What I want to do first is I want to cancel out that denominator of x2 minus x1 by multiplying both sides by x2 minus x1. And so this cancels out. And so I have this. I'll write the m first. I have m times x2 minus x1 equals y2 minus y1. Remember, m represents the slope of a line. x2, x1, y2, y1 represent the x and y coordinates of some point. Well, at this point, I don't really need to have these x1, x2s. I'm just going to rewrite it like this. I'm going to rewrite it as m times x minus x1 equals y minus y1. And I can do that because I can still tell the difference between x and x1. They're not the same. That's the whole point of these little 2's and 1's. And going back to the slope formula, the idea is you look at 2 points. You call one point x1, y1. You call the other point x2, y2. You plug in the coordinates. You do a little bit of arithmetic, and you have your slope. I'm not using this to find the slope. I'm using this to find an equation. So in this, from going forwards, I'm going to just x1 and y1 are going to represent the coordinates of some point, any point on a line, and x and y, I'm just going to leave as x and y, because in the end, I want an equation, not the slope. I want an equation, and an equation of a line needs to have an x and a y variable. So all I've really done is just change the way the equation looks. But it's essentially those two last steps are the same. Now, all I want to do is just kind of change the order, like write these up like this, to kind of switch the order of the sides. And what we have here is one of two common forms of what we call slope point form. However, what's probably a little more helpful to you is if I add y1 to both sides, and I write it like this, is y equals m times x minus x1 plus y1. So first of all, both these equations we call slope point form. And we can use these equations to find, or we use these formulas, I can say, to find the equation of any line, if all we know is a slope, which I keep highlighting in yellow, and some point, x, y coordinates. And the bottom one is probably the more useful too. And so again, let me just label this. Either of these are called slope point form. And you want to remember where the x1 and y1 I keep highlighting in blue, that is just some point on the line, any point on the line. And again, I'm not going to comment, I'm not going to write it down. M is the slope of that line. Okay, so as always, the best way of understanding this is to use it. And so let's use one of these two, right? I'll kind of focus on these here. All right, so here I have a line. And I want to find the equation of the line, and eventually I want to put it in slope-intercept form. But the problem is if I look at this equation here, the y-intercept I can't see right away. It's, here's the y-axis right here. The y-intercept is somewhere, I don't know, down here. I don't know where it is exactly. Now, I'm not saying I can't figure it out, but I want to show you how I don't need to figure it out directly to put the equation in slope-intercept form. The first thing I want to do is write down the last thing I did in the previous page, which is write down the slope point formula, or slope point form. All right, so for this, to use this, I need to find the slope, which I can do in a moment, and I need a single point. Well, let's first look at the slope. To find the slope of this line, I'm going to pick 2 points. How about this and this? Okay, I can tell the slope is negative, so I know m is going to be a negative number. But negative what? Well, I count down, what is that, 6 units, and over 1. So the slope is -6 divided by 1, or just -6. All right, so now I can rewrite my equation over here as negative 6 times x. Now I'm going to pause again. I need to pick a point. I just need to pick some point on this line. It doesn't really matter as long as I feel confident with the coordinates. I'm going to pick this point right here. And the point I just chose, looking at the coordinates carefully, is negative 4, comma 2. So negative 4 is going to be my x1, 2 is going to be my y1. It doesn't matter what point I pick. In the end, I'll get the same answer if I don't make any algebraic mistakes. But I might as well pick numbers that I feel pretty confident with. So when I go back to my equation here, I'm going to write negative 6 times x minus negative 4, which I'll adjust in a moment, plus 2. Negative 4 being the x coordinate, 2 being the y coordinate. Well, inside the brackets, x take away negative 4 is a slightly messy way of just saying x plus 4. I like that better. And now I just need to clean this up to put it in slope-intercept form. So I distribute the negative 6. And then combine these like terms at the end, which will give me my y-intercept. There we go. So that equation there is in slope-intercept form. The slope of negative 6 I could see really quickly by looking at my graph. I can now see the y-intercept. I can now actually see the y-intercept is negative 22. Remember I said it was down here somewhere? Well, now I know it's 22 units down. I found the y-intercept without directly finding the y-intercept, if that makes sense. I found the y-intercept by just doing something else, and eventually I saw it with my equation. All right. Notice a fair amount of algebraic steps there. Nothing crazy, but definitely we have to start feeling confident with this sort of algebraic work. All right, so let's look at the next one. Exact same idea. I want to find the equation in slope-intercept form. So looking at this right away, I can see the slope pretty quickly. I'll pick this point, and I'll pick this point. So I can see the slope goes up 2 and over 3, so the slope is 2/3. I know that pretty much right away. The y-intercept, I can see where it is roughly. I can see it's like right here. But where is that? It's between negative 3 and negative 4. It doesn't look like it's halfway. I mean, I can estimate, and that's not a terrible idea, but I don't want to estimate. So I want to know where that is. And so again, I can't see exactly where the y-intercept is, at least with confidence here. So I'm going to do the same thing I did last time, which is use this form. Keep in mind, I already know the slope. And so I know the slope is 2/3. For a point, I see to pick a point. I'm going to pick, let's pick this point right here. I'm going to pick that point right there because the y-coordinate is 0, which is a nice number. So this is at 5, 0. So I'm going to call x15 and y15. Sorry, y10. Again, if I don't make any algebraic mistakes, I'll get the same answer in the end for any point I pick. So I might as well pick numbers that I think are kind of pleasant. And so rewriting this equation here, I have y equals 2/3 x minus 5 plus 0. That's pretty nice, that plus 0. All right, so the plus 0 is kind of silly. At this point, I'm going to distribute the 2/3 and ignore that plus 0. So if y equals 2/3 x minus 2/3 times 5 is 10/3. Right? 2/3 times a whole number, top times the top, the bottom doesn't change, or you can think of it as 5/1. Other way, I'm done. There, I'm done. Now, that negative 10/3 is my y-intercept. If you change that to a to a mixed number, you get negative 2 1/3. So, sorry, negative 3 1/3. But again, I like 10/3 better in the equation, which is the same as negative 3.3 repeating. So that y-intercept, I now know exactly where it is. It's 3 1/3 units down, or 3.3 repeating units down. But again, negative 10/3 I actually would prefer for my equation than any of the two things I wrote down here in red. Okay, so in the end, this didn't need to have a lot of algebraic steps. All right, so let me give you a different type of question. Same idea in the end, except this time I want an equation in general form. But this time, instead of showing you the line, I've just shown you 2 points it goes through. All right, so I know my line goes through these 2 points here, 3, 4, 5, -1. What's the equation of the line in general form? Well, first, again, I'll get to general form in a bit. But first, let's just start with this, my slope point form. first thing I want to figure out is my slope. And I know my line goes through these 2 points. Now, it's not a bad idea to actually draw in here. I'm going to draw my line. If my line goes to these 2 points, I can visualize my line pretty well. So I'm going to grab a ruler here. Just draw on it. There we go. So there's my line. I can visualize it quite well. Again, my y-intercept is somewhere up, I don't know, near 10 or something. But I don't know where it is exactly. I have 2 points. So first let me find the slope. I'll just find the slope by looking at the graph. I go down 5 over 2. So the slope is negative 5 over 2. Okay, and then I need to pick, for that, after this, I just need to pick a point. I'm given 3, 4, and 5, negative 1. I'm going to pick 3, 4 because both these are positive coordinates. So I'm going to call 3 my x1 and 4 my y1. And now I'll go back here again. Now remember, I want my equation in the end to be in general form. Right now this is in slope point form, but I want it in general form. So at this point, let's remember what general form is. General form is when we have all our variables, all our terms on one side, so the equation equals 0. There's no fractions or decimals for any of my coefficients. My x term is positive. So for this, the first thing I want to do, I have lots of options, but I could distribute the negative 5/2. I could multiply by 2 right away. Maybe I'll distribute the negative 5/2 first. So if I do that, I have y equals negative 5 over 2x plus negative 5 over 2 times negative 3 is a positive number. And so I get plus 15 over 2. And then plus 4. Now at this point, I'm going to multiply everything by 2. Multiply both sides by 2 to cancel out my denominators. So my left-hand side, I have 2y. My right-hand side, when I multiply everything by 2, right, the whole side by 2, these denominators are going to cancel out. So I'm going to have just negative 5x plus 15 plus 8. Right, nothing for the 4 times 2, nothing cancels out. All right, I'm almost done actually. I just need to put everything on one side. I want my x term to be positive. So I'm going to bring everything to the left-hand side. I'm going to add 5x to both sides. I'm going to subtract 15 from both sides. Actually, before I do that, maybe I'll combine these two together right now. So altogether, that's 23. So I'm going to subtract 23 from both sides. So that cancels out, that cancels out. On my left-hand side, I have 5x plus 2y minus 23. On my right-hand side, I have nothing. So I write equals 0. And that's my equation in general form. Remember again, general form is not great for graphing. I said it's more useful for other things we'll do later on. But who cares about graphing? I mean, it's an equation, and that equation is correct. All right? So now the last question is an applied question. And I start with giving you a graph here showing you how the population of Canada has changed over the last 50 years. Okay? So we see here is showing how the population of Canada has changed from 1960 to about 2016 or so. And you can see by looking at it, it's not a perfectly straight line. This is the actual data for Canada, but it's pretty line-ish. I mean, if I grab my ruler here, I can approximate this really well with a line. There we go. What I just drew in red is a straight line, which really closely matches the actual data, which means for the last 50 years, so longer than any of us have been born, Canada has been growing in a very, very linear manner, a very predictable linear manner for these last 50 years. All right, so I can't exactly predict populations of Canada with a linear model, but I can model it and predict it quite well. I just can't be exact, but it should be quite a good prediction. All right, so next what I have is a graph of just 2 points of the data from above shown on this grid here. And notice on the x-axis, I have the years since 1960. On the y-axis, it's the population of Canada in millions. And I have 2 points, okay, for this little line segment here. And these 2 points are taken from the data I had above. So my first question is, what are the dates of the endpoints for this line segment? What's the date for this point and what's the date for this point? They represent actual dates. So this is about understanding the graph. And so if I look at this graph, this first point here has a 20. Actually, I'll highlight that in yellow. 20 for an x. And the second point has 50 for an x. So what do those mean? Well, it's 50 on the x-axis, but my x-axis is years since 1960. So this 20 is 20 years since 1960. So this is 1980. And this 50 right here is 50 years since 1960. So this is 2010. Okay, that's what those represent. And the y coordinates, 24.59, 34.01, those are the populations, the actual population of Canada during those 2 years. In the year 1980, Canada had roughly 24.5 million people. In the year 2010, it had roughly 34 million people. All right, so that's part A done. The main part of the question now is, let's imagine this line keeps going, and let's find an equation of that line, an equation that models the population of Canada over time. Now, I asked for it to eventually use the variables p for population and t for time. I'm going to start with just x and y, just because it's more familiar, but in the end I'm going to write it as population and time. So really I have a line here, and I have a line I want to find the equation of. And to find the equation of any line, I need a point. Well, I have 2 points. I need the slope. And I have 2 points here. I can find the slope. So let's start by finding the slope of this line up here. So to find the slope, I need to find the y2 minus y1 over x2 minus x1, or the vertical change divided by the horizontal change. In essence, for my slope, I need to go 34.01 minus 24.59 in the numerator over 50 minus 20. So, vertical change over horizontal change. So I get 9.42 over 30, which decimalizes to exactly 0.314. That's my slope. Okay, so that's the first part done. Next, all I need to do is pick a point. If I look back at my graph, I'm given 2 points. Why don't I just go with the first one? I'm going to use this and call this x1, y1. And I'm now going to use my slope point formula. And so again, I'm going to stick with x and y for now. And so my slope I know, and my point, I just picked one of those 2 points. Like I've said before, if you were to do this and pick the other point I gave you after 50 years from 1960, in the end you should get the same answer. Oh, and if you don't get the same answer, someone made a mistake. So now I said up here I want it in slope-intercept form. So let me put this in slope-intercept form. Let's distribute the 0.34. Again, I'm using real data here, so a calculator is always helpful. And then combine these two like terms. And I'm essentially done. I just have to change my variables in a moment. There's my equation. So putting this in the form I asked for, I can say, therefore, remember those 3 dots is a symbol for therefore. The population equals 0.314 times t for time instead of x plus 18.31, where 18.31 is my y-intercept and 0.314 is my slope, which leads me to the very last question, which is what do the slope and the y-intercept mean in this case? Now, because I'm using actual data, each of these means something that I should be able to express fairly clearly and concisely without rambling, without using any sort of complex vocabulary. So for example, the slope, 0.314. That is the average change of Canada's population per year. And so the slope is the average change or average increase in Canada's population each year. So even better than just this is to say, it's about 0.314 million. Maybe I'll make a little note up here, change in millions. So if you look at your graph, the y-axis is in millions. And so, that means about 314,000 people a year. 0.314 million is about 314,000. So that's what the slope represents. That 0.314 tells us on average, in the last 50 years, Canada's population has grown by about 314,000 people, 0.314 million. All right, that's what the slope means. And the y-intercept, which I've highlighted in pink up here, is 18.31. If I look back at my graph, that represents this point right here. Well, that's the population in 1960, because my graph starts time 0 is 1960. So that's it. That's the estimate, at least for the population of Canada in 1960. So the y-intercept represents, I'll say, because it is a it is a prediction. Y-intercept represents the population of Canada in 1960. And again, 1960 because that's the year on our graph that it starts at 1960. That was time 0. That's the start. In this case, it's about 18.3 million. About 18.3 million people. And while I don't expect that to be absolutely perfect, what the actual population of Canada was in 1960, I do expect it to be extremely close, and that's just because if I look back up here, this graph here did start in 1960, if you look very carefully, but the whole data, the way the data moves is linear. So my model, my prediction should be quite accurate. And if you can see this, it's the numbers are very small. This is my population in 1960, which is just shy of 20 million. So again, not surprisingly, our y-intercept for our model quite closely matches the actual data. All right, so that's it. One of the more involved lessons of the course in terms of algebraic work. But in the end, explaining what these things mean, if I'm applying this to some actual data, all this algebraic work represents something I should be able to explain. And now I'm done.